a binomial, you can approximate it by a normal, the envelope. So binomial, of course, x is binomial NP. That means probability of x equal to k is n choose k, p to the power k, q to the power n minus k. And its expected value, we saw it already, NP. Anybody knows what is the variance of this random variable? It's NPQ. You just need to work it out. Okay. And whereas the normal is going to look like this. So here, in fact, this is a standard normal, right, with parameter 1. So its characteristic function is e raised to minus omega squared by 2. So let's say this is y. So you are thinking, why will this look like that? So we will see. Whereas here the characteristic function is we already worked out there, p e raised to j omega plus q to the power n, right? So I'm going to show that instead of, so remember, some of the problems, attacking it directly may not be the best way. So I'm going to show that this characteristic function will begin to look like the normal characteristic function. And in fact, I'm going to do a simple, I'm going to start a simple transformation, and you'll see why. I'm going to work on this. Remember, x is binomial. So the other way relation is x equal to square root of npq y plus np, okay, right? X is binomial. What I'm going to show is that this is a normalized binomial. I'm subtracting the mean and dividing by the square root of variance. You may ask why. It's easier to show it on y. I'm going to show that y is going to look like normal. And then look at here. Then the logic is this way. If y is normal, then x is normal, because I'm only doing a linear transformation, right? I'm just adding a constant and scaling it. And we already saw that if this is normal, then this has to be normal, right? Under those conditions. So that's the way the proof goes. So of course it is not directly obvious, so something needs to be done. So let me start with the characteristic function of y here. So y, this is e raised to j omega y. But look here, y is given to be from here. So this is e raised to j omega x minus np over square root of npq. Now, I don't want, but if you have watched the video, there is no reason to do this. I have already done this in exactly the same way.
So how did you get y is equal to x minus np by root np?
It's not the same way. I'm just defining something to be y there. That's all. There's nothing to, if your confusion is, that's it. I can just define anything, right? X minus np over npq, just I have to define something, so call it y. That's not that y or something. Or you could call the z, I just didn't want to change everywhere, right? So then I substituted for x. Then you say this is a constant. I'm going to pull out all the constants outside. Right? See, remember, the expectation is only on the random quantity. Random quantity is the x here. So I leave the x here, and the other thing I pulled out. But look at this. X is binomial. So this is the characteristic function of x evaluated at. This is the characteristic function of x evaluated at this quantity. Instead of omega, it is omega over square root of npq. But phi x is given to us. We computed it earlier. See here, phi x is here. So I'm going to take that and substitute. So this is e raised to minus j np omega over square root of npq. Then you see here, p it, when you look at here, when I have omega here, I have this function. But there it's not omega over something. So this omega I'm going to replace by whatever is the variable there. So this is going to be p e raised to j omega over npq plus q to the power n, right? That's the characteristic function of this normalized binomial. Still we are dealing with the binomial. Now I'm going to bring this term inside here. So remember, this is already raised to the power n. When this comes inside, this n will go away, right? Because that's like something raised to the power n. So this is now going to look like p e raised to minus j p omega over npq square root. And there is already a term j omega, right, over npq. So I'm going to write it here. Then you have q e raised to minus j npq pq over, right, p omega over square root of npq to the power n, right? Is this true? I pull that term in. It is here, it is here. The reason I put, there is also, here you have also j omega. So I have j omega, because it is plus 1, I put a minus 1. But now you see omega is a constant. So omega goes outside. 1 minus p is q, right? So that's, I can write it as minus q, right? So let me make one more substitution here. So that's p e to the power j q omega over square root of npq plus q e to the power minus j p omega over square root of npq to the power n. Is this true? Remember, 1 minus p is q. So p minus 1 is minus q, minus minus plus. So I have j q omega, right? Now you expand. Remember, e raised to x is 1 plus x squared by 2 factorial, etc. So expand both the e terms. So this is now reads p multiplied by something plus q multiplied by something to the power n. So let's see what is inside. So this is 1 plus j q omega over over square root of npq, and then plus j squared q squared omega squared over, right, and plus higher order terms. Okay, here the same thing with the minus here and there. So this is jp omega over square root of npq. Then you have, so the next term is going to be plus, right? So plus j squared p squared omega squared over 2 npq plus higher order terms. Now let's add it up. P plus q is, the first term is 1, right? Then look at the next term. Here you have j pq omega. Here you have minus j pq omega, and the denominator is the same. So this term cancels with this term, right? J squared is minus 1. So both the places j squared is minus 1. Then you have, you see, pq squared omega squared. Here you have qp squared omega. So I can pull out pq is common, right? So pq is common. Then I have p plus q omega squared. In the denominator I have, so this is minus, right? J squared is minus. Then you have a 2 here. Is that right? Plus you have other terms involving n to the power 3 by 2 and so on, but the whole thing to the power n. PQ is common, right? See, you have a P here. I can pull out a Q, then still I have a Q here. If I pull out PQ, I have a P here. So I put the P plus Q here. But P plus Q is 1, PQ cancels. So this now reads 1 minus omega squared by 2n to the power n, right? 1 minus omega squared by 2n to the power n. But this is, of course, the expansion of e raised to minus omega squared by 2. As n goes to infinity, that's the only condition. So in a coin tossing experiment, if you keep tossing a large number of times, the result, you don't have to choose n, choose k, etc. You can approximate it by normal. Look at this. We started with a binomial characteristic function. We ended up with a normal characteristic function with the parameters 0 and 1. This is the same as what we had before. All right, so what we can conclude is this random variable y, this random variable behaves like a normal random variable with the 0 mean and variance 1. So look here, if y is normal with the 0 mean and unit 1, variance 1, again this is a linear transformation. So this has got mean NP and variance NPQ. In other words, x is also normal. So we started with binomial, we ended up with the normal. So the only condition is that the number of observations, number of trials have to be large.